And the slideshow from current slide, and the projector turned on. I think. There we go. All right, well, that's coming up. Let me make only one announcement I know about, and that is Alabama A&M has launched a grant from the National Science Foundation. It's a NOIS scholarship. And it's targeted to people just like you, people who are good in math or sciences, and think there might be a possibility, even though you may not have thought of it yet, that you might want to teach science or math in school, because we are woefully short of really good science and math teachers in school. So they are offering basically what it sounds like to me, an absolutely full ride scholarships your last 2 years if you, join that program, the North Scholarship Program. It is a great deal, okay? So give it a thought. You got the email just like I did, and so check it out, follow up, see what the requirements are, application process, deadlines, that kind of thing. I know UAB had a program, NOIS has been sponsoring these things for a while. UAB had a program. University of Alabama had one. Theirs were slightly different from each other, and sounds like they're slightly different for A&M's. So you have to check out the details to find out. And Tyra is here. No, I'm sorry, Krista is here. Sorry. Got it. Okay. Where did you go? Disappeared. There we go. We'll have class. Huh? Maybe we will have class. Okay. Any questions before we get going today? All right. Well, one thing I do want to bring up, I put it in the announcement and email, I'm pretty sure, didn't I, that we needed to talk about how to make up Tuesday's class, when to make it up. I'm going to make it up, but the question is, when do we want to do that? Now, you don't have to be here. The more that are here, the better. I'm going to record it just like I record all the other classes, and Q came in to hear this announcement. Good, thank you. Okay. All right. And so let me know when the most of you can participate, and that's when I'll do it. And Patel even decided to show today. Okay. And while I'm here, Thomas is here. Okay. Has anyone else come in while I was talking or getting my pen cap or whatever? Okay. So here are the possibilities. These are the times I'm free. There are not many of them, but there are some times. We got either Monday or Wednesday morning, 8, 8:30, whatever time you want it to be. I just have a class starting at 10, so no later than 8:30. Okay? Monday or Wednesday morning, that would work. Monday afternoon, anytime after 4, between 4 and 6. Okay? So starting at 4, starting at 5:30 or even 5:45. No, that's not right. 4:30 or 4:45, that would work. Okay? And the other option would be Friday morning, anytime between 8 and 12. Okay? Now, let's go one at a time. How many could make it Monday morning, anytime, but say 8:30? And let me get your name, please. Carla, right? I thought so. Now, finding you is the next issue. There you are. And got Asia. There. All right. Anyone else come in since I called roll? Okay, we're talking about the possible times to make up the class, so I'd like just a general count of how many could make all of these 4 times, any of these 4 times. Monday morning, 8:30, say. Nobody? 1, 2 people, okay? And is that, oh, 3? Okay. All right. Really anxious, eager back there, I can tell. Okay. So that's 3. Is Wednesday the same deal? Or can more of you make Wednesday? No. Okay. So we got 3 for Monday or Wednesday morning, 8:30. How about Monday afternoon, say 4 o'clock up to 5:30? Anybody? Monday afternoon, 4 to 5:30. Anytime in that time frame. Nobody. Okay? Or 1? Okay. All right. 3, okay, or 1. How about Friday morning? Anytime between 8 and 12. 1, 2, 3, 4. Oh, that looks like it carries. Okay? So let's plan for, is this Friday as good as any? As in tomorrow? Will it work? You tell me. 8:30? 9? 9:30? 10? Second? Second? 8:30? Okay. Which is? 8:30 or 9? 8:30? Can we go for 8:30? Okay, 8:30 tomorrow morning. Here. Oh, wait. How about us having it down in 255, the room we started in? Okay? Because that's a little closer to my office, and I have a feeling we aren't going to have more than 30 people here, will we?
So will it count business?
No. I'll record everything, and it'll be at YouTube videos, just like all the others are. Yeah. I'm sorry? I can't hear my. Yeah. See, I did. Yeah. And you see, we've already missed. Okay. First day of class, my wife had surgery, so it wasn't a full day that day. Then we had that day that we had tons of snow, if you remember, and we missed that one. And we missed last Tuesday, and believe it or not, we have coming up in April, Honors and Awards Day is just about always on a Thursday, okay? Now, we'll be able to have a little bit of class, but not a full class. So we're losing just way too many days. Usually Monday, Wednesdays are the bad days, but this term it turned out for me, this class, Tuesday and Thursday. All right. Quinn is here. If I can find you here. All right. So the class just decided to meet tomorrow morning, 8:30, right? Here, well, not here on this campus, but down in room 255. Is that okay? Everybody okay with 255? Y'all like this room a lot better, or it's just that room, the people in the back aren't so far back there, it's set up a little differently. And I don't think we'll have more than 30 people here. That room only holds 30. Can I count on a few of you not being here? Okay, all right. So we'll have class tomorrow morning to make up for the class we missed Tuesday. Okay? Good deal. Now, let me get the door closed so we can start going over. I know my voice interrupts everybody up and down the hall. People started wearing earmuffs even when it's warm outside. Okay. Any questions before we get started? All right. Then, where we left off last time, was there a question? Oh, I thought it was. Okay. Was on page 79. We're in chapter 1, function of the graph. We're almost getting through with this, folks. 1.8, combinations of functions, including composite functions, which is what we're doing now. And let me get from current slide. That's where I was going to go. This was example 5. We finished that. Let me make sure. All right, I think that's going to give us the most white space to work. We finished example 5. Let me get my pen set up. Okay. Here we're moving to example 6, top of page 79. If there are no questions, let's go for it. Find the domain of F composed with G. For those who weren't here, haven't been here, or haven't been listening to the videos, that means F composed with G. Sort of looks like a fog, doesn't it? That's not what it is, okay? For these functions, f of x is equal to x squared minus 9, and remind me your name? Huh? Tadarius, got it. All right. Now, sorry, I have to repeat this every time. In case you didn't realize it, or if you did, I was out Tuesday because I had a doctor's appointment. Could not avoid it. I had to be in the labs by 7:40. So, yeah, 7:40. I was there actually a little early, and the appointment went way past when it should have gone. So I was there till 9:45 or so. So my whole class was wiped out on Tuesday, and the class decided to let's try to make it up tomorrow. Tomorrow morning, 8:30, we'll be down in room 255, not this room, 255, and we'll make up this class. All right, g of x, we're doing example 6, top of page 79 in section 1.8. The g of x is equal to the square root of 9 minus x squared. Now, all it says is find the domain, okay? But they do more than that. They actually do it, which I think is a good idea. But let's start with the domain, all right? Now, remember, for a composite function, let's first tell me what that is. F composed with G. What's the definition of that? What does that mean? The other way to write that. Second, F, got it, of G of X. Okay, that's what it means. I think of that little circle there as not being fogged, but Jayla? Right, okay. Okay, I know you're in here. There you are. All right, anyone else come in since the call roll? Okay. Now, just so everybody hears this and will know, because I was out on Tuesday with a doctor's appointment, this class decided today the greatest number could make it tomorrow morning, 8:30, we'll make up that class. If you can be here, don't be here. Okay, let me, wait a minute. All right, okay. All right, I want to make sure it was you. All right. Start again. Because I was out on Tuesday, the class, the greatest number of people said they could make it up tomorrow morning, 8:30. Not here, down in room 255, okay? That room's a little bit better for instruction, I think, because it's not as long, and I don't think we'll have more than 30 people here. That room only holds 30, otherwise we'd be meeting down there, but since we exceeded 30, we moved here. So tomorrow morning, 8. All right. I think y'all will get the idea before it's over, won't you? Okay. All right. Get your name, please.
Kelly.
Say again. I'm sorry. Gotta find you. Yeah. Okay, good deal. Now, hit it one more time. Because I was out Tuesday and not here, and we didn't have class, we need to make up that class, and the largest number of students, the plurality we might say, said they could make it tomorrow morning, 8:30. Okay? So we will be not here, down in room 255, tomorrow morning, 8:30. If you can be here, be here. If you can't, it will be on YouTube video. And it should get loaded fairly easily sometime before noon on tomorrow. So you should be able to watch it anytime you can then. Okay, down in 255. See you there. Be there. Aloha. Okay, right. All right. Back to example 6, top of page 79. What they're asking for is the domain, but then what they're doing is more than that. So we started with what do we mean by the composition of F and G? F composed with G. That means F, and here's what I think of. It helps me remember. I think of the little circle there meaning of. F of G. So F of G of X. Okay? Now, when we're talking about the domain, domain's the input. Well, what's the innermost function? That's the G. What's the input for G? Ha! There's where the problem comes. That has a limited domain. So what do you think that might be? Anyone see it right off the top, or do we need to do some figuring on it? Second?
I think it's not like negative
2. Very good start there.
Is it 3?
2 positive 3. Excellent. Does everybody see that? Minus 3 less than or equal to x less than or equal to positive 3. Or the other way to put it in interval notation. How would I write that in interval notation? Bracket. Negative 3. Comma. 3. Bracket. Very good, because both of these include the equal sign. Now see why this is good. Very good there. Okay? If you had anything beyond that, say negative 4, what's negative 4 squared? 16. 9 minus 16? A negative number. You can't take the square root of a negative number. So you can't get any less than minus 3. Minus 3 will work right on the nose, right? Because minus 3 squared is 9. And 9 minus 9 is 0. You can't take the square root of 0. Fantastic. Okay? Anything beyond negative 3, this will be greater than 9. So you can't do it. Okay? And then anything between 3 and 3 will work. Right? Negative 3 and 3. 2 would work. 2.5 would work. 3 would work. But anything beyond 3 will not work, because that would be greater than 9. And then you would have a negative inside the radical. Can't do it. Not in the real number system. Okay. So this is the domain for G, which fits in here. Your answer to this is some positive number. Okay? And we don't even care what positive numbers, because the range of this, the answer here, becomes the domain for F. And guess what? F will take, let me... Oh, yeah, Mayfield, got it. Okay. I had to see you. Okay. I know, got you. Okay. And are y'all ready to hear it again? Okay. Here we go. Because I was out Tuesday and we didn't have class, we need to make up that class. Okay? And the plurality of students who were present at the time said the time that they could, the most people could do it would be tomorrow morning, 8:30. Now, if you can do it, fine. We won't be in this classroom. We'll be down in 255, okay? But if you can't be here, that's okay. It's not, you may have other things on your plate. So it will be in the YouTube videos, just like all the other classes have been and are, okay? It'll probably be loaded before noon on tomorrow, okay? So we'll be here. I'll be here. Normally I'm on Birmingham campus on Friday mornings. I'll give them a call today and tell them I'll be here. And I've got to send to my independent study, because those students usually go to the Birmingham campus, and tell them I'll be here. Okay. So, all right. So we determined the domain of this function is x between minus 3 and 3. And that's what feeds into this one. The output for that, some positive number, because this is a positive square root. And it'll be between 0 and 3, okay? All right. Name, please.
Kayla.
Huh? Kayla, got it. I need you, okay? Got it. All right. And here we go again. Okay. Because I was out on Tuesday, I may be out today too. Okay. Because I was out on Tuesday, we need to make up that class. It was my fault, not yours. And the most students that could do it said that they could do it tomorrow morning at 8:30. So if you can be here, please be here. Now, not in this room. Let's go down to 255. I don't think we'll have more than 30. Hold on. All right. I know you're in here. There you are. Okay. And by the way, great attendance today, folks. Fantastic. Okay? Let's hit it one more time. Because I was out on Tuesday, the greatest number of students who were present at the time we talked about this said that they would prefer to make up the test, or not test, make up the class, those who could, the most could do it, tomorrow morning at 8:30. Not in this room, but down in room 255. Okay? The one we started in the very first of the term. That room in the corner down there. So we'll be there 8:30 tomorrow morning. If you can be here, fantastic. If you can't be here, it'll be on YouTube video, hopefully by noon tomorrow. Okay? So if you can be here, it's really beneficial. You can ask questions. You actually interact. There you're just passive and sitting back and listening. But that's better than nothing. All right. Let's try it again. We're trying to find the domain of this function, f composed with g, of alpha of x being x squared minus 9, and g of x being the square root of 9 minus x squared. And we were looking for the domain where we first said, what do we mean by the composition of two functions? Well, I count this little circle there, which means composition of, to represent the word of, f of g. So f of g of x. So the domain is what goes in first, and that's the x for g, and we determined that was going to be between minus 3 and 3, inclusive. Okay? Then the output from this happens also to be between 0 and 3. Just happens to be the case here. Well, f will take anything. That would take all real numbers, yeah. The 3? This one here? Either one of those? She told me. Okay. No. Where? Well, we went through this, didn't we? If anything, okay, which one you want? Minus or plus? Both. Okay. Let's start with the minus here. Any value for x less than minus 3, just say minus 4. Okay? If you put it in here for g, you have the square root of 9 minus a negative 4 squared. A negative 4 squared is? Positive 16. 9 minus 16, negative 5. You can't take the square root of a negative number. So anything below negative 3. Negative 3 hits it right on the nose because negative 3 squared is 9. 9 minus 9 is 0. Can't get any more.
So you trial and error the numbers?
Say again?
So you're trial and error the numbers?
Okay, you could do that. I don't know how she did it. Just brilliance, I guess, you know. But here's how you could do it a little more formally. Now, this takes a little bit of effort, but we don't mind that, do we? We're hard workers, okay? What is inside the radical has to be positive, non-negative, okay? So let's say that. 9 minus x squared, rather all those words, what's the mathematical symbol that means that? Greater than or equal to 0. That means not negative, okay? Greater than means positive or equal to 0. Okay, so this thing has to be that. Well, this thing can be factored, can it? Okay, that factors is what? This thing right here. How does that factor? 3 minus x times 3 plus x. And that has to be greater than or equal to 0, right? Okay. Now, here we have a product of two numbers. Right? Okay. Now, how is a product of two numbers greater than 0? Two cases. Two cases. Product of two entities greater than 0. Either both of those numbers have to be positive, then that's greater than 0. Or both of them have to be negative. And then the product is still greater than or equal to 0. So we got two cases we have to consider. Whoa! What did I just do? My whole computer went black. Huh? Oh, that's still on. All right. Ah, okay, it came back. It went to Never Never Land. Okay. All right. So either of these two cases. So either 3 minus x greater than or equal to 0, and it must both be 3 plus x greater than or equal to 0. Okay? That will work, certainly. So how do we do this? How would you solve that first inequality there? Subtract 3 from both sides? Is that what I heard? Okay, I got it. All right, so that would be, these go away, minus x greater than or equal to minus 3. Oh, divide by negative 1, and that would give me x and a 3, right? What symbol do I put there? I left that out. Say again? Ha! Less than or equal to. Why? Right. Anytime you either multiply or divide by a negative number with a directional inequality, you flip the direction. Add or subtracting positive or negative doesn't change it at all. Multiplying or dividing positive number doesn't change it at all. Multiplying or dividing a negative number changes the sign. So here we got x less than or equal to 3. Now let's go up here and do a number line. I think we've done this before, haven't we? And put a 0 in the middle. And we'll put 1, 2, 3, 4, 5, blah, blah. Negative 1, 2, 3, 4, 5, blah, blah, blah. So here's negative 5, negative 4, negative 3, negative 2, negative 1, 0, 1, 2, 3, 4, 5, blah, blah, blah. Okay, get out of there. Okay. Now, how do we represent x less than or equal to 3? Well, there's 3. It can be equal to 3 and anything less than 3. Anything less than 3, that represents that, right? Now let's do the other side. Same way, subtract 3 from both sides. And now we're left with x greater than or equal to negative 3. Ha! Where's that? Well, there's negative 3 right there. Let's do this in a different color. What color would you like this one to be? Blue. Okay, I'm going to go dark blue. Okay? Anything greater than or equal to negative 3 would be anything this way, right? You got to have both because this was an and here. So that means it'll be between negative 3 and positive 3. That's where it comes from. Okay. Except we didn't do if both of them were negative. So let's do that if we can. And what we're going to do there is just change. Ooh, I thought I was changing. Okay, change the direction of this one, and that one, and that one, and that one, and that one. Almost sound like Bob Ross on the, no, never mind, we won't go there. Okay, y'all don't know who he is, do you? Okay, now, we're going to change these to, they all have to be less than or equal to 0. That would both make, if they're both less than 0, they're negative, the product will be positive. Okay, then we're going to, again, subtract 3 from both sides, and that leaves us this and that. Okay, but when we divide by negative 1, that flips us over to be that way, right? I like this screen now. I can just change them. You have to write it all down. Okay, now, let's do what we've got up here. So let's go back and erase some stuff if I can. I really made a mess of it, didn't I? All right, there we're back where we started from, kinda, if I can get my pen back. All right, let's do the first one there. X greater than or equal to 3. Well, that would be here, but it would be these x's out this way. And x less than or equal to negative 3 would be these x's this way. And guess what, folks? It's got to be both of those at the same time. Can't possibly be both at the same time because they have nothing in common, right? So therefore we go with the first one we had, which was this one. Okay, good deal. All right, that gave us our input for G, the domain for G. The output, by the way, is something between 0 and 3, only positive because that's positive. But it doesn't matter on the output of this because the output of this is the input of this. This would take any number in the world. So no limitation. So we're perfectly fine with that output because that will work for that input. So there, we've done what they asked, okay? However, they did more than this. So let's us do more than this too. So I'm going to erase this stuff, if that's okay. Did anyone need it any longer? I was hoping not, because I already erased too much of it. Okay. I can't get it to erase. There it goes. All right. So let's do what they ask us, find the composite of f with g. F of g of x. What you reckon we put in first? The innermost, the g of x. So this will be f of, and what is your g of x? The square root of 9 minus x squared. Okay? Now we're going to operate on that with the f function. What does the f function tell us to do? It says whatever is inside the parentheses here, you square it. And then you subtract 9 from it. So what is inside the parentheses here? The square root of 9 minus x squared. And what do we do with it? Square it, and then subtract 9 from that. What happens when you square a square root? They both go away, and you're left with 9 minus x squared, and then you subtract 9 from that, and what are you left with there? Negative x squared. Okay? Now, if that's all there was, you would say the domain was all real numbers. But it's not, because you're limited by the domain of that g here. This would indicate all real numbers, but you can't do that because it came from here. And you can't take anything outside of this. So the domain here is stuck to be that. And here's what it looks like. For those of you who don't have a book, on the graphical side, you have to be in this. That function that we have minus x squared, this is how it looks. Okay? But you are limited between minus 3 and 3, including the endpoints. They should have made a better definition there, except this is a picture of a graph, and the computer doesn't do that endpoint. So that is what we've got. Okay? If you see it, go for it. If you need to determine it, go for that too. It's all doable. Any questions on that? There is, by the way, a checkpoint. Please do your checkpoints as soon as you can after class, so you can reinforce it while it's fresh on your mind. All right. Now let's move on to any questions before I move on. All right. I'll get through. Here we go. In example 5 and 6, we formed the composition of two given functions. In calculus, it's also important to be able to identify two functions that make up a given composition. Okay? Here they were given the two functions, and you determined what the composite was. But in calculus, quite often you're given a big, ugly, hairy function and said, now let's undo that. For instance, here's a function. h of x is equal to 3x minus 5 raised to the third power. Well, that's actually a function inside a function, isn't it? This is a linear function, 3x minus 5, inside a cubing function. Cubed, right? So that's the composition of the outer function, the cubing function, and the inner function, that linear function. That is, h of x would be g of x cubed, which is this, which is f of g of x, which is f circle g. We're back in the fog again. Does that make sense? Now this process of figuring out what the functions that make up a composite are, basically you're decomposing a composite function. Okay? You're looking for the inner function first and then the outer function. In the function h that we just had, the inner function was your 3x minus 5 because that was inside together. The outer function was the cubic function. Okay? So that's how we did decomposing functions. Okay? They're skipping example 7. Let us do 7. And then if you want to, I'll tell you a dumb story. You care for a dumb story? Okay, we'll have a dumb story. Let's first decompose this function. Okay, and actually, quite often there's more than one way to do it. Write the function h of x, a different h of x, which is, we know to be 1 over x minus 2 squared, as a composition of two functions. They said 2. We could do 3, actually. So you tell me, where do you think we begin? Look for the inner piece. No. X minus 2. So let that be our g. G of x equal x minus 2. Then what do you think the f of x would be? The outer function would be, okay, you're doing 3 parts, and I like that, x squared. Then the third part, let's call it I of x, j of x, j of x, let's do that one. Then j of x, this is a composite of 3 function, would be what? 1 over x, the reciprocal function. And that would give it to us. Because the innermost is x minus 2, the next innermost is the squaring function, and then the last one is the reciprocal function. Or, they wanted just 2, you could put the x squared down here. And just have f of x equal 1 over x squared, that would do it for us. Or, you could have said the innermost was x minus 2 squared, and then the outer was 1 over x. So there's lots of different ways you could do it. Okay? Any of these would be correct. This is actually covers all the bases. It's a composite of 3. The problem, as they said, make it a composite of 2 functions. Okay? You just decomposed that function. Now, the book did the F function being x to the minus 2, and that took care of it. Okay? Or 1 over x squared. Okay? So they didn't do the last part. The exponent took care of that for them. Okay, there is a checkpoint there too. Now, you want a dumb story now? Okay. I'll try to keep it fast because we have lost too much time. But this ties across several disciplines here. One of these being music. Does anyone know who Beethoven was? I don't mean that great big hairy dog. That's a different story. Okay. Okay, Beethoven, musician. One of the greatest who ever lived. His Fifth Symphony, many people believe, is just the epitome of music. Okay? Da-da-da-da. You hear it all the time in all sorts of contexts. It's just a fantastic piece of music. Okay? It goes all over the place. It was radical when he did it. No one has ever, I don't think most people will say, ever come close to matching it. Fantastic composer. But you know, the music industry way back then was a lot like it is today. Can anyone tell me who won the Grammy 5 years ago? Now, you make a guess and you might get it right, but yeah, they changed. Right now, Ariana Grande is top of the heap, you know. But a few years ago, it was Beyonce. And she's still great, but, you know, it changes. Tastes change. You know, things change. And unfortunately, this happened with Beethoven, too. Even though he was, people today think one of the greatest composers who ever lived, after a while, people, you know, got tired of hearing just fantastic symphonies, so they wanted something else, chamber music or something light or something. And after a while, he wasn't able to sell his music as easily as he did at one time. And he was getting older, and it was harder to do. And guess what? Back then, no Social Security, no social safety nets, nothing to protect. And that's all he could do. I mean, he was a great composer, but he didn't have many other skills that were marketable. So he kept writing music. You know, he was getting older. It was harder to sell, but he was just full of music. Actually, as he got older, he actually went deaf. And that's a terrible thing for a musician. So what did he do? He cut the legs off of his piano so it would sit square on the floor. He sat on the floor, and he heard the music by the vibrations through the floor and still wrote fantastic music. Unbelievable how great this guy was. But he couldn't sell anything. So by the time he finally died, he was a pauper. And evidently didn't have any family or none left, or I don't know. And they found him dead in his place he was renting to live. And no one could claim the body, so they buried him in the pauper's field, you know, the potter's field. Just where they put people who didn't have family and couldn't afford it, they just buried him. Well, as often happens, a few years later, people said, you know, yeah, this little chamber music is all nice and stuff, but, you know, it doesn't hold a candle to good old Beethoven's symphonies. Hey, whatever happened to Beethoven? I haven't heard of him lately. What happened? So they went looking, found out he had died. He died? Well, where's he buried? In the potter's field? No, that will never do. He was the greatest musician that ever lived. We got to give him a proper burial. We got to do that. So they had to go through all the legal paperwork to exhume the casket, to get him up so they could put him in a place and have a monument there, you know, and just really honor this man who had done so much. So they finally got all the paperwork done and stuff. So had hired someone to go dig it up. He was hiring and stuff. And then they were lifting it up. And then right about the time they got it to the top, the guy dropped it, his end of it, and the lid popped open. And there sat Beethoven erasing scores of sheet music like crazy. What was he doing? Decomposing. Oh! That's what we just did. We decomposed a function. All right. Y'all wanted a dumb story. You got it. Aloha. Okay. Never mind. Okay. All right. So let's go to applications. All right. The number N of bacteria in a refrigerated food is given by N of T, and this T is a capital T. And in physics, if you ever go this far, you'll find out capital T usually stands for temperature. Okay? So capital T is temperature. So the number of bacteria N as a basis of temperature is 20 T squared. This is a weird-looking function, but it's here. And this is good only for a range of 2 to 14 degrees T. Now, these are degrees Celsius. So don't think, wow, this is cold. Okay, because this is refrigerated, not frozen. So these would be, this is 2 degrees above freezing, which would be about 35, 36 degrees Fahrenheit. So that's about what your refrigerator runs at. Okay? It doesn't freeze food, it just keeps it cold. Okay? Now, what you've done, you've taken this out of the refrigerator. It was refrigerated, and this is the number of bacteria as a basis of temperature. So as you bring it out and the temperature rises, the number of bacteria goes up. Okay? That makes sense, doesn't it? Because bacteria don't do much when it's cold, but once it gets warmer, they get more active and they eat more, so they grow and reproduce. So T is the temperature of the food in degrees Celsius. When the food is removed from the refrigeration, that's what I just said, the temperature of the food is given by, now here's a temperature as a function of time. Little t is time, capital T is temperature. So as you bring it out of the refrigerator, the temperature of the food starts going up, right? And here's the function that defines that, okay? 4t plus 2. Now this is only good for 0 to 3, okay? And here's sort of the reason for that. Does anyone know approximately what 14 degrees Celsius is? Roughly, that's getting probably pretty close to 60 degrees. Okay? Maybe a little less, okay? And this is the time it takes for this to get up to 60 or so. Just plug it in and see. When T equals 0, what do you have here? The temperature would be 2. Ah, there it is. When T is equal to 3, the temperature would be 14. So this makes sense. These things fit, okay? Where T is the time in hours. So in other words, leave it out more than 3 hours, it's rose to nearly room temperature. Maybe not quite, but close to it. And the bugs have been growing like crazy. Okay, the bacteria. Okay. So find that's why the mama says, better get that turkey in the fridge after Thanksgiving meal. You don't want to leave it out there too long. Okay. So what we're finding here is a composition N composed with T, that one, of T. And interpret the meaning and context. So let's first do what they said, N composed with T as a function of the capital T is temperature, little t is time. What does N composed with T mean? What's the definition there? N of T of little t. And what do we plug in first? The T of T, okay? Well, this will be N of, the little t is 4t plus 2, right? Okay. Now this is going to take a little bit of room, so I'm going to move upstairs and do it a little bit. The N function up here takes what's inside and starts with the number 20, multiplies it by the square of what's inside, then subtracts 80 times what's inside, and then adds 500 to it. Right? What's that? Okay. The N function, it says N operating on this input T, the temperature. It starts with the number 20, and then takes whatever's inside this parentheses here and squares it. Right? That's what it did. Subtract from that 80 times what's inside the parentheses, and then add 500 to that. And that will give you the number of bacteria. Well, now what's inside parentheses is this thing. Not just T anymore, but what T is. 4T plus 2. So what would the N function tell you to do? Where do we start? 20. Okay, it'll be 20 times 4t plus 2 squared minus 80 times 4t plus 2 plus 500. All right. We got to square that 4t plus 2. Can anyone sort of do it in your head, or do you need to go out and foil it? Either way is fine. Okay, wait, let me start up here now. 20 times, okay, you said 16 t squared, okay.
Plus 8.
Plus 4.
Wait, how is him?
Second? Where did you get the 16t? Twice the product of these, yes. Remember, it's the square of the first, twice the product, square of the last. Oh, yeah, okay. So twice the product will be 16t plus 4. Got it. Okay, that's the first part. Minus 8. Well, we can go on and multiply that. What's 80 times 4t plus 2? Okay, wait, let me get my pen back. That would be minus 320. Is that what I heard you say?
Yeah.
T minus 160 plus 500. Whew. Whoa, get back here. Okay. Got it? Any questions? Everybody got it? Now, did you see how we did this and why we did it? I gave you a little rule, but if you don't remember the rule, I don't like rules that much. So sometimes I just go off to the side and pull it. 4t plus 2 times 4t plus 2. 4t times 4t is 16t squared. And then the outer would be 4t times 2 would be 8t, but the inner would be 8t, so that's where you double it. 8t plus 8t is 16t, and then square the last. Okay, the last, okay? That was finger waving. Okay. Now, let's clear the parentheses there. This is getting really crowded, isn't it? 20 times 16 would be 320 t squared, right? Plus 320 t from 20 times that 16, plus 80, right? 20 times 4 is 80, minus 320t from before, minus 160 from before, plus 500 from the very beginning. Okay? Now we need to combine some like terms. You see any? Ooh, positive 320t minus 320t, they add to 0. I like that. And then the rest of them are your constants. So you have 580 on the positive side, subtract from that 160, that would leave 420, right? Got it? Okay. So let's see, what did we wind up with? Here's some space, I'll put it here. So the n of little t now, what we've done down here is going to be 320 little t squared plus 4, what? 420. Okay. Whoa, get back here. Okay. That's going to be your capital N as a function now of little t. So what's that? Goodness gracious. Okay. What that is, okay, we've done the first part. We found the composition, there it is, okay, of capital N composed with, capital N composed with capital T of little t. Now, interpret the meaning. What is that telling us? This was telling us the number of bacteria as a function of temperature. What is this one telling us?
The number of bacteria.
As a function of time, exactly. The longer you have it out there, the more the bacteria is growing. And by the way, at t equals 0, which we could have here, what's the number of bacteria? 420. So when you first pull it out of the fridge, it's already got 420. Yeah, everything has bacteria in it. Everything. That water has not much, but a little bit of bacteria. Everything does. Most of the time we can handle those. A lot of times it may be beneficial, but we don't know. But anyway, so start off with that. But as time goes by, you're squaring that. Boy, by the time that becomes 9 times this plus that, you got a bunch of bacteria. Better get that turkey in the fridge. Okay. Now, we've done that. The B part says, find the time when the bacteria count reaches 2,000. It started at 420. When does it reach 2,000? Now, how are we going to do that? Anyone got an idea? I'm going to erase a little bit of space here so we can do this more easily. I'm going to use that space up there, I think. Or maybe, since I don't need it anymore, we've already done this, so let me use this space. That's a bigger white space. If I can get it to erase, it's not, there it goes. Okay. Find the time when the bacteria count reaches 2,000. How are we going to do that? Yes. Okay. The time is represented by what? Little t. And the number of bacteria is represented by what? Capital N. Well, here we have it. There's a capital N, so let's put 2,000 in there, right? Is equal to, get back here, okay, 320 t squared, there's our little t, back here, okay, I lost it, plus 420. Hey, there's an equation, one unknown. I think we can do this, can't we? How would you begin? Okay, subtract what, 420 from both sides? I like that idea. Oh, if I could write, I would like it even better. Okay. 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 I think I'm going to erase the line below it too now so we can keep writing. Come on, get out of there. There we go. Okay. All right, that gives us 420 from 2,000 would be 1,580, right? Equal 320 times t squared, right? What do we do next? Second? You saying something about squared? Not yet. Second? Divide by 320. Okay. All right. I have a feeling it's not going to be a very pretty number, but what will it be? T squared is equal to, someone with a calculator, 580 divided by 320. Or if you want to be really lazy about it, say again? 375, is that what you said? 375. On the nose? Second?
4.9375.
Oh, wait. Okay, wait. Okay. I was going to say that sounded incredible. Okay. I didn't think it could possibly be true. Okay, 4 point, is that what you said?
9375.
9375. Okay. So that's t squared. I'm really not interested in what t squared is. I want to know what t is.
So, let me ask you,
Yes.
why didn't you get rid of the, oh, never mind.
Good.
Part of the equation.
Yeah. Okay.
Okay.
So how do we get rid of the square?
By square root.
Take a square root. And what do you get then? Say again? 2.22 hours, because t is measured in hours. I don't usually measure hours in 0.22. Okay, so what I'm going to do is take that 0.22 of how many minutes is in an hour? 60 times 60, and that would be 132, right? So 13 minutes. So the time would be about 2 hours and 13 minutes, I think, if I did it right. Okay? All right. Well, they just left it 2.2. All right, that's how we did it. Let's see how they did it. How are we doing on time? I don't have my watch with me today. Oh, we got plenty of time. We just had people leaving early. All right. So here's how we began. We first did the composition of n with t, and that's n of t, okay, which is n function said you start with 20, take whatever's in, they left off this part. They should have put 4t plus 2 here rather than t of t. But that's okay. Take what's in here, 4t plus 2, square it, then subtract 80 times what's in here, which is 4t plus 2, and then add 500. Just like we did. Okay, just not as organized as we were, okay? Now, they did the square and the binomial, just like we did, and they distributed that, just like we did. All right, then they have to clear their parentheses here, and that gave them a 320t squared plus 320t plus 80 minus 320t minus 160 plus 500. Fantastic. Then you note that the positive and negative, that just happened in this problem. It doesn't always happen. Don't bank on it, okay? And that brought us down to 320t squared plus 420, okay, is equal to n of t of t. And what that means, that's the composite function went from being the number of bacteria as a function of temperature, and then using the temperature as a function of time, composing those two together, you get number of bacteria as a function of time, not temperature. Represent the number of bacteria in the food as a function of the amount of time since the food has been pulled out of the fridge. Okay? Now, when the bacteria count will reach 2,000, just plug it in, plug it in. The 2,000 number of bacteria, solve for T. And that's what we got. They got 2.2 hours. They weren't as precise as you were. That would be about 2 hours and 12 minutes. We said 13. Okay. Or something like that. Got it? Any questions? Make sense? Okay. Maybe you need to ruminate on it. Okay. All right. there is a checkpoint there that you can certainly do. Okay? I think this is the last. Oh, wait. Note that when you solve this equation, what are you doing? Okay. You reject the negative value. Oh, yeah. Because when you take the square root, it's always plus or minus. Well, what does it mean to be a minus time? That has no meaning. So you throw away, you don't even consider the minus. I forgot that, yeah. Whoa, okay. So let's now do, any questions on 1.8? Let's now do the vocabulary. Two functions, f and g, can be combined by the arithmetic operations of blank, 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 and blank. What three arithmetic operations? Addition? Yeah, exactly, okay, to create new functions. And the blank of the function f with the function g is f little circle g of x, which means f of g of x. What does that mean? Composition. Perfect, okay. You can do homework exercise number 3. It should be at calcchat.com. Then do any of the odds, 5 through 11. They should all be at CalcChat. 11's at CalcView. Do any of the odds 13 to 23. They're all at CalcChat. 13's at CalcView. Do either 25 or 27. They're both at CalcChat. 25's at CalcView. Do any of the odds 29 to 33. They're all at CalcChat. 33's at CalcView. Do any of the odds 35 to 41. They're all at CalcChat. 35's at CalcView. Do number 43. It's the only one like that. Do either, and it should be at CalcChat. Do either 45 or 47. They should both be at CalcChat. 45's at CalcView. Do any of the odds 49 to 55. They should all be at CalcChat. 49's at CalcView. There's some applied problems. You can do any of these you want. Any of the odds 57 through 63. Okay? They should all be at CalcChat. Then there's a true-false, 65. Look at that, think through it, understand why it's either true or false. Okay? Then 67 is a problem you probably could do. And if you're really into proofs, you can do 69. Writing functions would be 71, and another proof, 73. Those are only if you want to. All right, the last section we're going to cover before the test, which is coming up soon now, so get those quizzes in, is going to be 1.9. So let's advance to that. What's that? Yeah, if I can get them all in, I want to go over them with you. Okay? What you can do, though, is see me after class or anytime during office hours, and I'll go over them with them individually. But I can't return them to you until I get them all in. So, folks, if you don't have them in, get them in so the other folks, everybody can see what they may have missed, if you missed anything. Okay? So, please, folks, get those quizzes in. I hate it when I can't get them back to you, but I can't until I get them all in. All right, 1.9, and we've got we've got 9 minutes left. Okay. And here we go, waiting for a PowerPoint. Kind of hot in here, isn't it? All this brain power going to work here. It's pretty amazing. Okay. What we have here, for some reason, font size, I don't care about font size. There we go. Okay. Wait. Slideshow. Current slide. Okay, we're still in Chapter 1, but we're soon going to be over. Functions and their graphs. And now at 1.9 is inverse functions. Now, we've already been dealing, in fact, you've been dealing most of your life with inverse functions, but you probably never called them that. Okay? So, what was the first operation you learned way back in school a long, long time ago? Addition. And once you finally got through all those cards and things and stuff and thought, hey, I got math down now, what did they turn around and do? Have you subtract, which undid addition. Subtraction is the inverse operation of addition. So way back there in grammar school, maybe even in kindergarten, you were doing inverse functions, though you didn't even call them functions, and you didn't know they were inverses. Later you did, and what undid that? Division. There you had another one. Later you raised things to a power, and then later you took a Square root or roots, yeah. So you've been doing inverse functions all along. So what we're going to do is find inverse functions informally, which I find sort of a waste of time, and verify that the two functions are inverse functions of each other. That's worth doing, okay? You'll use graphs of functions to determine whether the function have inverse functions or not. That's pretty useful, and we'll come up with a brand new test. Before, to determine if it's function, we had the vertical line test. Now, to determine if it can have an inverse, you do the horizontal test as well. And that's going to tell you whether the functions are one-to-one. That's going to be the test of whether they have an inverse. And then we'll find the inverse functions algebraically. That's going to be the fun part. Okay. Say again? Okay. So, starting with inverse functions. We know that a set of ordered pairs can represent a function. Remember, that's one of four ways. Okay, there's graphing, there's saying verbally, vertically, or something like that. And then there's writing a formula or equation. But an ordered pair will work. For instance, this function, that's written as an algebraic expression, f of x is x plus 4. If you only had a limited domain of 1, 2, 3, and 4, what would be the range of that? If your domain was 1, 2, 3, and 4. 5, 6, 7, and 8. Yes, there is your B. So, there's your input, there's your output. Now, so it follows that the function x plus 4 will be this set of ordered pairs. For that domain in this range, 1, 5, 2, 6, 3, 7, 4, 8. Now, if we interchange the first and the second coordinates of each of those ordered pairs, you would have what we call an inverse function. That would be, let me change those two, 5, 1, 6, 2, 7, 3, 8, 4. You've just reversed the order of that. Now, what algebraic function would have done that for you? Would have taken a 5 and made it a 1, taken a 6 and make it a 2, taken a 7 and make it a 3, taken an 8 and make it a 4. What algebraic function would do that for you? Subtract 4 from it, x minus 4. That would be the inverse function of this one. And like we already said, the inverse of addition is subtraction that you did back in grammar school. So you've just done your first inverse function. Now, here's how we represent it. F to the minus 1. Now before, when that was a number or a variable, like x to the minus 1, 3 to the minus 1, what do we have a little bit earlier? We had x to the minus 2. What that minus, superscript minus, meant was do a reciprocal, right? That's not what it means when it's a function. If that's a function raised to the minus 1, that doesn't mean do a reciprocal. That means the inverse function of. So it's an old way of expressing something with a new meaning. If that's a function name there to the minus 1, it always means inverse function. Okay. Now, that new one is a function that takes set B as your input, your domain, and maps it onto set A, which is your range. So it reversed everything. And it can now be written as followed. The inverse function of f, like you said, was x minus 4. Y'all got it right? And that would be this set of ordered pairs, 5, 1, 6, 2, 7, 3, 8, 4. Just like y'all said. Now, note that the domain of f is equal to the range of f inverse, because the range of f inverse, 1, 2, 3, 4, is the same as the domain of f. That was 1, 2, 3, 4, and vice versa. The domain of f inverse, 5, 6, 7, 8, was the range of f. Okay. Also note that the functions f and f inverse have the effect of undoing each other. So not only does f inverse undo f, if you went and took f and operated on this again, you would, let's see. Well, we won't go there yet. We'll come back and do that. So, here is, this is an ordered pairs or equations. This other way to express a function is a mapping. here's the domain of f. You're starting with f, and the f function is f of x is x plus 4. You only had 4 values in this domain, 1, 2, 3, and 4. You operated on those and got your range of f, which is 5, 6, 7, 8. So those are only numbers over here. But your inverse function takes this as a domain and maps them right back to where you started. 1, 2, 3, 4. Now, here's what you did. If you did f operating on x, and then f inverse operating on f, you wind up with x in it. Oh, wait. Okay? That works. And if you had done it the other way, you'd wind up right back at x again. And this is the one, and for now, only time that f of f inverse and f inverse of f, when you compose two functions, remember we said they don't give you the same answer if you reverse the order? Now they do. And if they give you x, that means they're inverse functions of each other. So we just have discovered a way of detecting inverse functions, identifying inverse functions. I take it by the motion that we must be out of time. Is that right? All right. So we will begin next time with example 1. Okay? No new homework exercises here. We'll move on to 1.9. Hopefully we'll get it done next time. If we do, and that's going to be tomorrow, right? If we finish this tomorrow, that means we're ready for the test on Tuesday. Now, if we don't finish it tomorrow, then we'll have the test probably on Thursday. Okay? So watch your YouTube video to find out whether the test is Tuesday or not. Okay? All right. Good deal.
This one look amazing.
All right. Good deal. All right. Did you get a copy of the quiz? Okay. Whoa. All right. Now, if you have so, hold on just a second. I'm getting a copy of the quiz. Whoa. Do you need graph paper? Yes? All right.
I have a copy of the quiz.
You didn't get one?
No, I wouldn't have anything.
Okay. Now, somehow, I wound up, some people must have gotten 2 copies because I had enough run off. I don't have any more. Let me run down to the copy room and make a copy. Oh, wait. There is one. No, it isn't. I think I can have it. That's my last one. Do you need graph paper? Okay. Okay.
Thank you.
All right.
And when do you have free time today?
Hardly any. Oh, paper topic, great. I have 15 minutes between this and my next class, 15 between that and the next class, 30 minutes between that and your class, and then...
Can I see the test?
Second?
Can I see my test?
The quiz? Okay, can you do it right before or right after the class we have this afternoon? Let's do it then, because we'll have more time then. Because I've got to get down to my other class right now. Okay. All right. I'll get out of here soon, folks. Okay.
Tomorrow at 8:30.
Tomorrow, 8:30. Okay.